Let's look into how an FIR filter can be designed with the so-called windowing method. This is only one method to design an FIR filter, but it offers interesting insights into the possibilities and limitations of FIR filter design. For this, we start with the specification of an ideal low-pass filter in the frequency domain, here given in normalized frequency. Keep in mind that we want to design a discrete time filter, hence our specification has to be periodic. We know already that we will not be able to design a causal filter meeting this ideal specification, but by deriving the realistic and causal filter step by step, we will see how each step, approximation or simplification affects the filter. Corresponding to the ideal discrete time low-pass filter specification in the frequency domain S of omega is a discrete time sinc function in the time domain. The sinc can also be seen as coefficient Cn of the continuous time Fourier series applied to the continuous periodic function S of omega in the frequency domain. In any case, if we want to achieve the ideal low-pass filter with frequency response S of omega, the impulse response would have to be equal to the discrete time sinc, here denoted as Cn. But of course this would lead to a non-causal filter, since the coefficients Cn for n less than 0 are not equal to 0, and to a filter with infinite range, since the sinc has infinite range. So a way to overcome this difficulty is to use a finite amount of those coefficients indexed with non-negative values of n to achieve a causal finite impulse response filter. As we want to design an n-tab filter, we will hence take the coefficient Cn for n equals 0 up until n-1. If we compare the frequency response of the filter h of omega obtained from those tabs with the specification of our desired filter S of omega, we see that h of omega has a lot of ripples. Also, h of omega in the stop band is not even close to 0, and the gain of h of omega in large parts of the pass band is not much different to the gain in the stop band. So the question is, why did we achieve such a bad filter, despite the fact that we started with the coefficients of the ideal filter specification? The answer lies in understanding which tabs we have selected. Since we have selected the tabs between 0 and n-1, this can be interpreted as multiplying the infinite amount of coefficients Cn with a rectangular window of length n times Ts in order to extract exactly n samples. In the frequency response, this corresponds to convolving the ideal filter specification S of omega with a sinc function with 0 crossings at multiples of 2 pi divided by n Ts. But since the rectangular window is not symmetric but instead has been shifted to the right by n Ts half, its frequency response has to be multiplied with e to the power of minus j omega Tsn half. So h of omega is the convolution of the purely real-valued specification S of omega, and e to the power of minus j omega Tsn half times w of omega, where w denotes the window function, which is here a rectangular window. Convolving a purely real signal with a complex signal, due to the multiplication with a complex exponential here, creates phase distortions, which explains the very poor performance of our filter h of omega compared to the ideal specification S of omega. So as I said earlier, this filter design of taking the first n coefficient Cn is not the best choice, as it corresponds to using an asymmetric window. It should be a much better choice to take a symmetric window w of t, so here a symmetric rectangle in between minus nts half and plus nts half, and then shift the symmetric tabs to the right in order to achieve a causal filter, so that the filter tabs hn are a symmetric and shifted part of the discrete time sinc. And the frequency response of the symmetric window w of t is a purely real-valued function w of omega, here a sinc. Not surprisingly, the frequency response of this filter is much better compared to the first filter we derived, as its performance is much closer to the performance of the ideal filter S of omega. Since in the time domain we have taken a symmetric window w and then shifted the tabs after the multiplication, in the frequency domain h of omega is obtained by first convolving the purely real-valued S of omega with a now purely real-valued w of omega, and then multiplying with a complex exponential e to the power of minus j omega Tsn half. So only two real-valued functions have to be convolved, which avoids the phase distortion leading to the poor filter performance seen in the previous example. and the shifting of the symmetric taps after the windowing results in the multiplication with a complex exponential in the frequency domain. However, this multiplication doesn't affect or distort the convolution and only results in the phase angle minus omega TSN half, which is a linear function of omega. Hence, FIR filters are also often called linear phase filters. So by using symmetric and shifted taps, we can already achieve a huge performance improvement. But the magnitude of the frequency response of the obtained filter still has ripples in the pass band and in the stop band. Those ripples result from the convolution with the sinc function, which is the frequency response of the rectangular window that we have used in the time domain. So if we want to reduce the ripples of our filter in the frequency domain, we have to choose a window in the time domain whose frequency response has less ripples in the frequency domain. One such choice would be to use a triangular window before shifting the taps. The resulting taps Hn are hence scaled down by the sides of the triangle, which affects most the taps close to 0 and close to n-1. Since the frequency response of the triangular window is the sinc squared in the frequency domain, which has much smaller ripples but a wider peak, the frequency response of the filter when using a triangular window has smaller ripples but a slower roll-off due to the wider peak. A very good choice is the Hamming window, which is one full period of a cosine slightly scaled and shifted upwards. Its big advantage is that its frequency response has almost no ripples. The peak has the same width as the peak of the sinc squared, resulting from the triangular window. Hence, when using a Hamming window to derive the taps in the time domain, the resulting frequency response of the filter has almost no ripples in the pass or the stop band, and the roll-off of the filter or the width of its transition band is similar to the roll-off of a filter achieved from using a triangular window.